Okay, this one's going to be a little bit more fun. It says, use what you know about geometric sequences to find the value of the missing term. So we don't know what the 12th term is. We want to know the 12th. We know the 6th and we know the 10th. Okay, we talked about this, but let's take a different approach. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if the 10th term is 108, 11, 12, and this is what I'm solving for, and I know the 6th term, 1, 2, 3, 4, 5, 6, is 48. How do I get to here, right? Keep in mind, geometric sequences, it's constant multiplication, right? It's an exponential process as opposed to a linear process. So to get from this term to this term, I would multiply by r. Then at this term, I would multiply by r to get to here. I would multiply by r to get to here. I would multiply by r to get to there. So essentially what I'm doing is I'm taking 48, multiplying it times the common ratio to the 4th power, and that gets me to 108. Okay, so this is spelling it out and looking at it as that repeated process. So I could take this, multiply it times 4r, or multiply it times r 4 times to get that. What this is illustrating is the same idea that we've shown in previous examples, and that is, if I know the 10th term and I know the 6th term, I can multiply the 6th term times the common ratio 4 times to get the 10th term. As long as this subscript and this power add to be this, I'm gravy as far as geometric sequences are concerned. So, gravy's excellent. That's what I meant, I'm excellent, because gravy's awesome. Gravy's awesome with everything. Except probably like, I don't know, cereal. Anyway, if I'm solving for r in this case, because that's going to help me get to here. If I know the common ratio, I can multiply this by that 2 times to get to there, right? That's going to get me to that term that I'm looking for. So if I divide both sides here by 48, I get r to the 4th power equals, oh gosh, what is that? 9/4. Okay, probably 2.25 on the calculator. All right. Then, in order to get r by itself, I've got to take the 4th root. Okay, I can take the 4th root of both of these sides, also known as taking 9/4 to the 1/4 power. Right? If you want to take a 4th root, if you want to take any root that's not a square root, you can raise it to that fractional power. Okay. And this, I had this written down. R, in this case, 9 is not a perfect, I don't even know, quartic, I don't know what you would call that. I wrote this number down, 1.2247. So R is approximately 1.2247 as my common ratio. Okay, and that's an approximation, that's not exact. But now that I know what the common ratio is, if I want to take that to get the 12th term, right, let's set up one of these equations again. The 12th term in a geometric sequence, I could use the 10th term and multiply times the common ratio how many times? 2 times, right? So the 12th term can be found by taking 108, which is the 10th term, and multiplying it by this squared. Okay. Now, just something also on the side which is kind of interesting. I'm going to put this out there because this is pre-calc honors. 9/4, that's really this raised to the 1/4 power. Think about that for a second. Okay, just a different perspective on this problem. 9 and 4 are both perfect squares. They're not both perfect fourths, or whatever you would want to call that, okay? But they are perfect squares. So I could write this like that. And what do we do with powers of powers? Right? We multiply them. So this would become 3 to the 2/4, which is 1/2 over 2 to the 1/2. And that, watch this. That is the same as the square root of 3 over the square root of 2. So this is another way of looking at the common ratio. Right, that's what I was doing to calculate the common ratio, was taking the 4th power of that. I just manipulated that with exponent properties to get the square root of 3 over the square root of 2. So this is a different representation of the common ratio. If you type that into your calculator, you'll get that 1.2247 or whatever decimal that was. So if that's the common ratio, then I put that there. What happens when I square it, right? The radical goes away. I end up with a sub 12 equals 108 times 3/2, and we get, instead of the decimal, we get the actual answer, which is 162. Okay, you would have gotten something close to 162, I'm sure, if we had left that as the 1.2247, which is fine. Okay, but I just wanted to give it a different approach using exponent properties in the same manner. Okay.